In this video, we considered a Poisson distribution. The Poisson distribution is used to model the number of events that occur in a given time period, where the number of events in a given time period is constant. This distribution can be applied to spatial and other domains as well. Examples include things like the number of floods, fires, or stock market drops in a year, or some other unit of time. It includes the number of flaws in a square yard of cloth or in a meter of wire and the like. It's also used for arrivals as well. For example, how many customers per hour, how many cars arrive per day, how many tows arrive at a lock per month. Other examples include those here. Counts from a surface divided into equal sections, the number of flaws in a surface, the number of defects per linear unit, for example, of wire, cable, or rope, the number of things per unit, pathogens per serving, fish caught in a day, the number of defects per unit, cavities per person, people suffering from a disease, or the number of anything per unit, for example, graduates from a university, vacancies on the Supreme Court, labor strikes per year, those sorts of things. Here you see the density function, small f of x, and the cumulative distribution, large f of x. Once again, you see a string of x values. Notice there is one parameter here, lambda. Otherwise, we have the data itself or the known constant e. We use the formula here for the density function along with the lambda value, in this case 5, to calculate f of x. Because this is a discrete random variable, this f of x does have meaning. So the probability of obtaining 1 from a Poisson distribution with a mean or lambda of 5 is 3%, as you see here. This is the probability of obtaining 2 flaws in a square meter of cloth that has an average of 5 flaws per square meter. So these values do have meaning, unlike those that we encountered in the continuous distributions. One other little sometimes interesting fact is that the probabilities of f of x increase. 3%, 8%, 14, 17.5, up to lambda. And then once you get numbers larger than lambda, they begin to decrease. The distribution has one parameter, lambda, and lambda can assume any value, any positive value, and it's the mean of the distribution. So let's have a look at risk. We are looking for the Poisson distribution, and it comes up with one parameter. Must be greater than 0, and it is the mean. So change that from 1 to 10, and you can see the probabilities increasing up to lambda. They peak at lambda, and then they begin to decrease. The Poisson distribution is a discrete distribution, and it returns only integer values greater than or equal to 0. The ratio of its mean to its variance always equals 1. Let's scroll down here a little bit, and we want to consider this feature of the distribution right now. If lambda is the mean time between events, as used by the exponential distribution, then lambda equals 1 over the beta. Beta is the parameter for the exponential distribution. So for example, if you get one customer every 10 minutes, if an exponential distribution has a beta of 10, then the customer arrival rate is 1 divided by beta, or 1/10 per minute. If we want to model the number of customers per hour, then we would use 60 times 1/10, or a Poisson of 6. So let's have a look down here now. The time between customers is 10 minutes. So let's take a look at this distribution here. This is an exponential distribution with a beta of 10. So this would give you the distribution of time between customers. So there's 9 minutes between customers, 11 minutes, 6 minutes, and so on. The arrival rate, lambda, is 1 divided by 10, or 1/10 per minute. And if we take a look at this distribution now, we have a lambda of 0.1, and you can see at least the 0, 1 here. 0, the most likely outcome, 1, considerably less likely, and if we scrolled on out to 2 and higher numbers, we would see a vanishing probability for those values. If we were interested in the arrival rate for 60 minutes, this is 60 times 0.1, or 6. And here is the distribution that would give us the arrival rate for 60 minutes. We have a lambda of 6, and you can see now how many customers you might expect in 60 minutes. In a similar fashion, if we want to know how many arrive in a work shift of 480 minutes, that's 1/10 times 480, or a lambda of 48. And so we have a Poisson distribution that has an average arrival of 48, and this picture right now is showing you a picture of what you might expect in your shift. You expect 48. There's some probability, it's rather small, that you could have as few as 30 customers. There's some probability rather small that you could have as many as 70. But this is a picture of the variability that you would encounter in your workplace. The Poisson distribution is very useful in risk analysis, and the number of examples is large. The Poisson distribution has a useful property that I want to demonstrate down here now. Oops, excuse me. Maybe we'll go over here. The Poisson distribution property is that Poisson of A, so if we have customers per day shift, where lambda is 50, so let's let that lambda, some value A, be 50 for the day shift. Then we have a Poisson distribution here with lambda of 50. Now we have some other lambda, let's call it B. In this case, let it be 23 customers. The night shift has an average of 23 customers, and you can see that here. So we have the variability, the variation that you could expect with that lambda of 23, and you saw the variation with the lambda of 50. Well, as it turns out, this property is Poisson of A plus Poisson of B is equal to a Poisson of A plus B. So this variation plus this variation, 50 plus 23, is exactly this, a lambda of 73. This single distribution describes the sum of the variation in the other two distributions. So this property is saying in words that if A customers are expected to happen in some period, like the day shift, and B customers occur in another period, like the night shift, we could estimate the variation of the total number of customers in the total periods, shift day plus shift night, with a Poisson of A or B. Excuse me, A and B. My mistake. So we would add the two together. The Poisson distribution is often thought of as being applied only to rare events, and this is not correct. It can be applied to common events as well, as the examples above suggest. The Poisson distribution is related to the exponential and the gamma distributions through the Poisson process, and that was named after the French mathematician and physicist Simeon Denis Poisson.